In a previous video highlighting various locations near the lunar South Pole that could be used for different use cases, I mentioned Mons Mouton as a possible location for large-scale commercial operations. In this video, I want to make a proposal for developing this region as an economic hub for lunar startups. The purpose is to demonstrate a way to develop this location in a lunar startup-friendly way that directly supports new lunar companies. So, let me introduce you to this idea. Mons Mouton shallow mining concept. My proposal is to use Mons Mouton for shallow mining of 1% of the total surface area. By excavating and processing only to a depth of 100 meters, no deep drilling tech is required. This region is mostly flat with only gentle slopes, making it easy for rovers to move around and transport equipment and regolith over the surface. Excavation of this area will liberate between 12 and 22 billion tons of feedstock for use in lunar base and infrastructure construction. If most of the material is loose regolith, the estimate will be towards the lower end. If consolidated hard rock is present within the first 100 meters, then the estimated yield is higher. A mid-range value that's realistic for a depth of 100 meters or below is around 20 billion tons. The top layers, perhaps the first 10 to 20 meters, can be scooped up to extract volatiles such as oxygen, helium-3 and argon. As we will see later in this video, argon is a key resource. Below this level, more sophisticated techniques will be needed, requiring the use of drilling rigs and quarrying techniques. The amount of aluminium that can be mined from this region far exceeds Earth mines, which produce around 70 million tons per year. Mons Mouton, at least for infrastructure, will largely be constructed using aluminium with lunar silicon used for solar panels. Smaller amounts of iron and titanium can be mined for specialized uses. Regolith, with the addition of binders or by microwave sintering, can be used for road surfaces, lunar paths or for lining tunnels, as we'll see later. Modest mining tech, along with some NASA dust mitigation strategies, can liberate billions of tons of regolith for infrastructure and commercial uses, and in the case of helium-3, for sale back on Earth. Shallow mining advantages. Shallow mining will bootstrap a large amount of lunar metals and oxygen from the regolith. Excavated areas can be converted into pressurized tunnels for use in subsurface transportation, linking processing centers to habitats and landing pads. One key piece of technology to convert lunar soil and rocks into valuable metals is a lunar foundry. Lunar Industries, a space startup I've covered on this channel before, is already working on this idea. Their lunar foundry can process between 50 to 200 tons of feedstock per year, requiring between 10 to 100 kilowatts of power per foundry. Once operational, it can produce beams, drill rig bodies, tunnel support bolts, aluminium wiring, panels for habitation modules, and rails for a lunar rail network. A high voltage DC microgrid will be used to power all of the facilities using aluminium wiring from the lunar foundry. Mons Mouton, due to its geology, is 10 to 18% aluminium by weight, so it can be sourced easily. An essential facility that needs to be constructed quickly is a gigawatt-scale solar farm. This is needed to power the electric drilling rigs, excavators, foundries, and processing facilities. Sandvik mining equipment. Before we get into the tunneling specifics, let's first examine Earth equipment that can be used with only minor modifications for the Moon. Sandvik produces heavyweight mining equipment for underground tunneling. They have an impressive portfolio of equipment that translates remarkably well for lunar tunnel construction, especially for the shallow mining concept proposed here. They manufacture a range of battery electric vehicles with full autonomy or teleoperated modes of operation and produce zero emissions. Some of their mining rigs can move 6 kilometers even on inclined slopes on a single battery charge. Batteries can be hot swapped in minutes, allowing for almost 24/7 operations. They have vehicles specifically designed for rock bolting and ground support. This is an essential task as tunnel walls and ceilings must be stabilized to protect against moonquakes or loose rocks. Their electric rigs have inbuilt cooling loops supporting operations in a vacuum with perhaps no modification, or at most modest increases in the size of radiator panels. In a lunar tunnel, the temperature is a constant minus 20 degrees Celsius day or night, which aids in reducing overheating. These electric drilling rigs have full autonomy due to Sandvik's auto-mine technology, teleoperation from a pressurized surface control center at Mons Mouton, or from a lunar station or even Earth. Private Wi-Fi with a 4G, 5G mesh network supports real-time telemetry, supporting traffic management and helping to avoid collisions. Teleoperated operations avoids humans needing to work in their tunnels directly. Autonomous electric loaders can haul excavated materials to the surface for processing. The gigawatt-scale surface solar farms will recharge the battery packs, allowing the mining vehicles to work continuously. No ventilation or cooling is needed, which simplifies operations and reduces power consumption. The tunneling scenario explained next assumes electric vehicles teleoperated from a Plateau control center. Dust mitigation is handled with NASA's developed electrodynamic dust shields powered by a gigawatt solar farm. Tunneling sequence. The operations needed are for surface excavation of loose soil and rocks, followed by drilling of underground tunnels, which can then be pressurized and used for habitation, storage, or subsurface transportation. The first operation is vacuum drilling using electric rigs. There are pros and cons for drilling in a vacuum or within a pressurized space. It's simpler to drill in a vacuum and also safer. Heat is dissipated using radiators, allowing Sandvik electric vehicles to perform well in a vacuum. Dust can be mitigated by adding electrodynamic dust shields developed by NASA. These can be fitted to the electric rigs or to the walls of the tunnel. These shields can remove over 90 to 95% of the dust, including extremely fine dust from the tunnels, and operate at low kilowatt power. It's crucial to immediately reinforce the tunnel after drilling to avoid cave-ins or falling rocks. This is done with a rock bolting vehicle which drills aluminium rock bolts into the tunnel walls. Mesh sheets are pinned to the walls and ceiling secured with bolts, followed by spraying shotcrete on the walls. This seals any micro cracks to avoid leaks and adds compressive strength to the tunnel. By sealing a tunnel section every 10 meters, excavated areas can be pressurized and inhabited sooner, resulting in a quicker return on investment. Each tunnel segment is fully isolated by airlocks, supporting a safety-first approach to lunar habitation and preventing any cascade failures. Tunnel pressurization. Why argon is better than nitrogen. Tunnels are sealed and pressurized in 10-meter segments with a diameter of 5 meters. Each tunnel section is isolated with airlocks on both sides. Liners are manufactured from Regolith materials and inserted into the tunnel, providing an airtight seal. The tunnel is pressurized with a 50-50 mix of oxygen and argon at 0.5 atmospheres. This is breathable and reduces fire risk even in oxygen-rich environments. Argon is ideal for industrial facilities such as a foundry or processing centers, as high temperatures are present, which can cause nitrogen to react, forming nitrides. Both argon and nitrogen are present only in trace amounts in lunar regolith, but argon is easier and therefore cheaper to collect in practice. Argon extraction on the Moon. Interloon, a lunar space startup, have plans to extract helium-3 by sifting large volumes of regolith. This will naturally result in capturing argon as a byproduct. It's not the primary resource for Interloon, but would make a second revenue stream for the company or any lunar resource startup excavating lunar soil, as it can be sold to other operators for pressurizing habitats and tunnels. Argon is non-reactive, so it only needs to be separated from other volatiles before it can be sold, making it relatively simple and cheap to collect. It's likely all lunar startups which are excavating lunar regolith will sell argon and other resources commercially to offset their costs and provide alternative revenue streams. For one tunnel segment, around 80 kilos of argon is needed. This requires excavating about 2,500 tons of regolith. A single interloon excavator can process 100 tons of regolith per hour, so it would take about a day to process enough material for one tunnel segment. The company, to be commercially viable, will need to process millions of tons of regolith for helium-3 extraction, resulting in large quantities of argon being collected. This means argon will be available commercially in large amounts, making tunnel pressurization costs low. Interlune's business plan aligns well with a commercial base at Mons Mouton. Although this location doesn't have high yields of helium-3 like the equator regions, the lower operational cost due to shared infrastructure, power and resources make it compelling. Interlune could use this space for pilot and small-scale operations. Once their equipment has been perfected, they can move to locations with higher yields. In the meantime, Argon and other volatiles can be sold to other lunar operators to generate alternative revenue streams. Other companies such as Magna Petra also plan to mine helium-3. Ethos Space Resources plans to produce lunar oxygen, and likely Blue Origin and SpaceX at some point will excavate lunar regolith to extract valuable lunar metals and volatiles. These companies clustering at a single commercial hub could share infrastructure, power, communications, and resources, and buy and sell to each other, kickstarting a lunar economy. Tunnel sections. Let's look at a tunnel section which has an internal diameter of 5 meters and a length of 10 meters. Each section has 7 rings of 13 aluminium rock bolts to stabilize the surrounding area for a total of 91 bolts. The main HVDC, that is high voltage direct current trunk cable, will be connected to each tunnel section by a dedicated riser to the surface. This riser doubles as a ventilation duct and carries a bundle of cables for fiber optic internet connections, telemetry, power and water return. Each tunnel section has its own local battery rack to provide 60 minutes of emergency power in case of loss of surface power. This gives crew time to suit up and exit the tunnel to the surface while still having lighting, power, life support and communications. Powering the tunnel's high voltage direct current power grid. The plateau has near constant sunlight, and with high elevation there are no shadows cast from other lunar features, making Mons Mouton an ideal location for massive solar farms in the gigawatt range. Solar panels on the moon are up to 13 times more efficient than Earth due to no weather losses. An early task will be to set up a high voltage DC microgrid to power all facilities, vehicles and completed tunnels. Aluminium wiring, which can distribute power across kilometers with high efficiency, can be fabricated from lunar regolith. With gigawatts of power available, widespread use of NASA's electrodynamic dust shields, which run at very low power, would be trivial. This would keep moon dust away from facilities and to stop the fouling of rovers, radiator panels, other critical equipment. From the main DC trunk link, cables will run to each tunnel section using the ventilation risers. Honeybee Robotics have single lunar masts capable of 100 kilowatts of solar power each, so gigawatt scale solar farms is easily achievable even for an early commercial base. Less than 3 square kilometers of land would be required for a gigawatt scale farm. The plateau has a surface area of over 7,800 square kilometers, so huge amounts of power can easily be generated at this location. Aluminium is abundant across the plateau, and lunar foundries can extract it with high yields, over 85% in lab tests, with some processes approaching 100%. An aluminium wired DC microgrid aligns with NASA's plans for building a lunar base. Tunnel segment, 10 meters by 5 meter diameter, bill of materials. What materials are needed for a tunnel segment and how much is required? Let's look at the bill of materials for a 10 meter length tunnel that's 5 meters in diameter, pressurized with a 50-50 mix of oxygen and argon at 0.5 atmospheres. Approximately 2.8 tons of aluminium is needed. Almost a ton is needed for the mesh sheets around the tunnel walls and ceiling. A further 400 kilos for bolts to stabilize the surrounding rock. Another ton of aluminium for an airlock frame, with minor amounts for pipes, drainage channels, ventilation duct and more. Regolith-derived materials such as the shotcrete used to stabilize the rock wall require about 76 tons of material. 63 kilos of oxygen is needed, which is abundant, and 63 kilos of argon, which can easily be captured and separated from any regolith processing operation. Other smaller components such as pumps, sensors, battery packs, and specialized diamond cutters for the drilling rigs will need to be supplied from Earth. Final thoughts. Shallow mining of even a tiny fraction of the Mons Mouton plateau would provide vast resources for kickstarting a commercial hub on the moon. Every lunar startup can benefit from locating there, even the helium-3 miners. The concentration of lunar infrastructure, processing facilities, gigawatt-scale solar farms, power grid, lunar road network, and landing pads would make it unbeatable. In addition, lunar operators will find buyers for their services or products quickly, helping to offset operating costs while they scale. What do you think of the idea of using Mons Mouton Plateau as a commercial lunar hub? Could shallow mining of the area provide all the resources needed to kickstart a lunar economy? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning, depending where you watch from. The live stream is a great way for you to share your thoughts and opinions on the videos I posted this week or on any space topic in general. I highlight the most thought-provoking comments on videos I've received, along with previews of upcoming content. If you got the time, please tune in and say hi. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.